let us understand SHM as projection of uniform circular motion on a plane. So over here we take it as a body, this is XY plane, and over here this is a body which is rotating in circle. Let's say this is moving in a circle of radius r with a constant angular velocity. So this motion is uniform circular motion. So over here we don't have any alpha or angular acceleration. The body is moving with a uniform angular velocity. That is, either we say what is the average angular velocity or instantaneous angular velocity, that is one and the same thing. So over here when this body is rotating like this, and over here we have put a screen like the screen of a cinema hall, and from here is a rectilinear propagation of light, and this light is moving in a straight line. That is, we are talking about the rectilinear propagation of light. So obviously when this is moving like this, and this is a particle, some mass which is moving in this circle with the constant angular velocity. So when it is over here, then it obstructs this light, and as a result a shadow is projected over here, a shadow is created over here. As it moves, when it moves over here, this only obstructs this ray only, and as a result the shadow is over here. When it is over here, the shadow is over here, and when it comes over here, then once again the shadow is over here. When it is over here, shadow is here. When it is here, shadow is here. When it is here, shadow is here. When it is here, shadow is here. When it comes over here, the shadow is over here. As a result, when this moves in circle, this shadow moves on this vertical plane. It moves like this. So as a result, when this moves one circle, this moves from here to here, here to here, here to here. When this circle, one circle is completed, then one oscillation of this is completed. That is how the motion takes place is this goes like this, and it keeps on moving. So like this motion or this motion, we say because projection of this uniform circular motion on a plane, so this motion is SHM, this is uniform circular motion. Projection of this motion onto the screen, that is SHM. Similarly, when we say it is moving like this, so projection is like this, or we can also say that is this is also like a motion of when a mass is attached to a spring vertically hanging and it is displaced like this and released. So this is moving within the extremities of plus A and minus A, that is equal to R. So when this is the mean position, so this is the mean position, this is the mean position. What is the maximum displacement of mean position? That is equal to R only. So this is amplitude is going to be R only. So once again when it reaches over here, the displacement of the mean position is amplitude is equal to R only. So this is the mean position, this is projection is SHM, and this can be very much related to this, that is this is also SHM. So SHM is projection of uniform circular motion on a plane. Now what we see over here is when the light is projected over here, then over here this has some velocity, over here it momentarily comes to a stop, over here it momentarily comes to a stop, then once again reaches over here with maximum velocity, then the velocity reduces, once again comes to a stop and coming back to the mean position. So obviously during this motion the velocity is changing, so it means there is some acceleration also. Now we are interested in what is the displacement of particle from the mean position as a function of time, and how we can relate it to this uniform circular motion. Now we know that this body is moving with angular velocity omega. Let's say at time t, this reaches over here. So this is R. So this is R. This is going to displacement. We call it as y. Once we start our observation from point P, and this body is moving with constant angular velocity omega, then let's say at time t, it reaches over here. When it reaches over here, this subtends at angle theta at the center with the positive x-axis. So if this is R, so this is R cos theta and this is R sin theta. So it means from the mean position now the shadow has reached over here. The shadow is here. What is the displacement of this shadow from the mean position? So this is y. And what is y? Y is equal to R sin theta. Now we also know that is angular velocity is equal to theta by t. So many radians per second. So theta comes out to be omega t. We can put it over here. So y is equal to R sin omega t. So displacement is represented by simple single harmonic function, that is sine function. So y is equal to R sin omega t. Now we observe that is the velocity is always varying. It is always changing during this motion. It's over here, it has some velocity over here, it comes to a stop, once again comes over here, once again comes to a stop. So it means the velocity is varying. So velocity is not constant. How we can find this velocity? This velocity and acceleration we can find it using calculus also and alternative method, that is without using calculus methods also. So let's understand first how we can do it without calculus method. So over here we see that is when the particle is moving like this in omega, so this velocity, tangential velocity, is obviously going to be r omega. We have done it in our rotational mechanics also number of times, and circular motion also we have understood it. If there is any confusion, you can please revisit those lectures, and once you are through with this, then once again you can come over here. So this velocity is equal to r omega. Now the point to be noted is that this velocity has two components. One is this, the other is this. If this is theta, this line and this line, they are parallel lines, right? So let me remove this. So I have removed the unnecessary details for a time being. So if this is theta, this line and this line is parallel, so this is theta, this and this is 90 degree. So if this is theta, this is 90 minus theta, and this is going to be theta. Also we have done, that is angle between the two lines is same. What is the angle between the perpendiculars? Or the angle between the perpendiculars is same as the angle between two intersecting lines. If we see, this line is perpendicular to this line, and this line is at angle of 90 degree to this. So whatsoever is the angle between these two, the same is going to be angle between these two. So now this velocity can be broken into two parts. One is r omega cos theta, and this is r omega sin theta, right? So once again, theta is equal to omega t. So we can call it as r omega cos omega t, and this is going to be r omega sin omega t. Now point to be noted is, that is over here when we see the velocity along the y-axis, and when the light is being projected from here, that is projection of uniform circular motion on a plane, the point to be noted is this velocity component, which is parallel to the light, it will not be visible onto the screen. It is something like, if a point mass is over here, so its shadow is here. When it moves with whatsoever velocity it moves in this direction, it may be 10 meter per second, 20 meter per second, but the shadow of this will still be over here. So we'll see that the shadow is still over here. So whatsoever is the velocity in this direction, the shadow will not move. So it means that is we shall be seeing on the screen this component of velocity, and this component which is parallel to light will not be seen on the screen. So velocity which is going to be seen is over here, and this velocity is going to be, the velocity function is going to be r omega cos omega t, right? So this is going to be, if we say put it like this, so it is r omega, we can put it as 1 minus sin square omega t, because we know sin square theta plus cos square theta is equal to 1, cos theta is equal to 1 minus sin square theta under root. So similarly over here, cos omega t, we have put it as sin square theta, and this is omega t, so this comes like this. If you take r inside this square root, so this comes out to be omega r square minus r square sin square omega t. So this comes out to be omega r square minus, but what is r sin omega t? This is, so this comes out to be r sin omega t its whole square, and this comes out to be r sin omega t. We know r sin omega t is y only minus y square. So velocity function is omega under root r square minus y square, or we say velocity function is r omega cos omega t. This omega, which is called also called angular frequency or angular velocity of this uniform circular motion, obviously the units are radian per second. So if this body is moving with angular velocity omega, then if someone says that is what is the velocity at time t, then you can use this function. This is velocity as a function of time t. But if someone says what is the velocity when the body has moved so much distance from the mean position, that is that it has displaced from this mean position, then what is the velocity? Then you can use this expression, that is v is equal to omega r square minus y square. The thing to be noted is that is v is equal to omega r square minus y square. It's so omega is constant, r is constant, r is obviously the amplitude also. Omega is angular velocity or angular frequency, and y is the displacement from mean position. As it is going from here to here, y over here is changing, and at the extreme position y becomes equal to r. So over here y becomes equal to r. When the y becomes equal to r, so v comes omega r square minus r square, that is it becomes equal to 0. That is at the extreme position, this particle momentarily, this body which is executing SHM momentarily comes to a stop. Otherwise also, if you see, that is over here right now, when it reaches over here at the extreme position, this velocity is parallel to light. that is parallel to the projection. So it means we will not see any velocity component when it reaches the extreme position, and same thing is visible over here. When the y becomes equal to r, the velocity which is seen over here, that becomes equal to 0. Whereas when the particle is at the mean position, this body which is executing SHM is at the mean position, then velocity is in this direction. It doesn't have any component along this way. The whole component is cutting these lines. This whole velocity will be seen over here, and once over here and over here also. This velocity is perpendicular to the rectilinear propagation of light, that is, this velocity is perpendicular to the rays of light. So that's why the whole velocity will be seen over here, that is at the mean position. This is going to be, velocity is going to maximum. That is, the whole component, the whole velocity will be observed over here. That is, at the mean position, the velocity which is going to be seen, observed on the screen is going to be r omega. Even if we use this expression, that is v is equal to omega r square minus y square, at the mean position y is equal to 0. So it means v is equal to omega r square minus 0 square, that is omega into r. That is same thing what we have just understood in terms of SHM being projection of uniform circular motion on a plane. So we observe that is velocity at the mean position is maximum, and at the extreme positions the velocity becomes equal to 0 momentarily.